So I'm going to talk about a project called HALO7D that's just starting out. So I won't have a lot of results. I'll talk about a project that promises to produce exciting results. This all started because I made a discovery a few years ago that we live inside a galaxy. When that happened, I started to look at some of the foreground things that we were throwing away otherwise. And so I'll talk about the HALO7D project, but I'll also give you a few related examples. The main theme of the HALO7D project is the Milky Way's stellar halo. And if we can measure the motions of individual stars in the Milky Way stellar halo, 60 motions. 60 phase space, positions, three positional dimensions, 3 velocity dimensions. Then we might have some handle on using them as tracers of the dark matter halo. We also want to use these stars to look for substructure, try and understand the accretion history. And in the process of doing this, the spectra we're taking are going to tell us something about the chemical abundances of the stars, not just iron to hydrogen, but also the alpha to iron ratios. So I'll briefly touch upon 3 ongoing studies. Like I said, the HALO7D survey of the candles fields that many of you know about kicked off this spring. I'll say a little bit about that, show some example spectra from that, hopefully illustrating the diagnostic power of these spectra. I'll say a little bit about how HALO7D started. It really started in the foreground of Andromeda. SPLASH is the spectroscopic and photometric landscape of Andromeda stellar halo. And the trash from SPLASH, which we've now pulled out of the dustbin, can tell us something about the foreground substructure in the Milky Way. Alice Deason talked about this on Tuesday. And similarly, in another large survey, this is the next generation Virgo survey, photometric and spectroscopic survey of galaxies in the Virgo cluster, galaxies, globular clusters of the Virgo cluster. The foreground can tell us a lot about substructure in the Milky Way. All right, so there are 2 components to the HALO7D program. There is an HST archival legacy program that involves taking literally every field for which HST has taken deep multi-epoch images with its new cameras. We're not using WIFPIC 2 or WIFPIC 1. We're using ACS and Wide Field Camera 3. As long as there's a baseline of 5 or more years, and as long as one of the 2 epochs is deep, then we can abuse the distant galaxies in a particularly special way here. We can use the background galaxies as wallpaper, and it's like it's analogous to trying to watch an insect crawl slowly across the wall. If it's a completely white wall with just the rare nail holes spaced very sparsely, it's very difficult to judge the subtle motion of an insect. If, on the other hand, the wall is not completely white but has subtle wallpaper painted onto it, then it's much easier to look at the motion of, even a subtle motion of that insect against this background wallpaper. That's what we're using. So that's why one of the epochs needs to be deep to map out the background galaxies. We expect to measure proper motions for about 1,000 main sequence turn-off stars in the Milky Way halo, ranging in distance from few or 10 kiloparsecs out to over 100 kiloparsecs from the sun. This is an incredibly subtle measurement, but HST has done this a few times already. And just to give you a sense of how subtle this motion is, the motion of stars across the face of these galaxies is analogous to watching human hair grow on the surface of the moon as seen from the Earth. That is exactly how subtle the motion is. But with a long enough baseline, this is doable. Sort of encouraged by the success of this legacy program that was led by Roland van der Marel at Space Telescope Science Institute, Alice Deason led the charge to putting in a complementary Keck DMOS spectroscopic program. Alice did a lot of the work on the proposal, and this is This has involved a fairly large team of people. I've got their names down here, but I wanted to highlight in particular the work of Emily Cunningham, who's a PhD student here at Santa Cruz. And her work is, her PhD thesis is going to be on the foreground stars for which we're making both the HST and spectroscopic measurements. Now, we realize these stars are faint. We're talking about 10 to 100 kiloparsecs. We're talking about stars that are faint, stars that are relatively hot. When stars get relatively hot, their absorption lines get washed out. These are stars that are about as hot as the sun or even hotter. Faint, hot, and relatively metal poor. So these three things make for a very difficult combination because the absorption lines are weak, the spectra are noisy, and it requires very long integration times with even with the Keck telescope with DEMA spectrograph. So we planned this survey with somewhere between 8 to 32-hour integrations of DEMOS masks. Typically per mask we get 20 to 30 Milky Way stars. They don't fill the DEMOS mask. A DEMOS mask can easily hold 150 objects. So we fill the rest of the masks with distant galaxies. So when our survey is done, we should have really high quality spectra of about 350 main sequence turn-off stars in 3 of the northern candles fields. So the Cosmos field, the Goods North field, and the extended growth strip. As an extension to that survey this fall, we're going to look at foreground stars in the direction of Andromeda, and there our fillers are going to be Andromeda red giants. I'll talk about that briefly. We hope to measure radial velocities from the spectra of the foreground stars. We hope to measure chemical abundances. And by using a combination of spectroscopic and photometric information, we hope to be able to pin down their line of sight distances, because that's one of the 6 parameters we're trying to measure for these stars. It's called HALO7D because the 7th parameter stands for some flavor of chemical abundance. All right, let me show you some sample spectra. Emily's been working very hard on this. This is from one of the fields, one of the masks in one of the fields. This is from the extended growth strip. This is a little over 6 hours of integration, relatively good condition. And lo and behold, our very first object, instead of being a turn-off star in the Milky Way, turned out to be a quasar. So here it is. We're horrified, right, because 1 in 1, and astronomers like to extrapolate. We figured all 24 of our objects on this mask would be quasars. But thankfully, the contamination rate is something like 15 to 20%. It's not that bad. We expected this. These are relatively blue objects. They're point-like. Anyway, here's a pair of stars. I'll just say a quick word about these 2 stars. These are 2 main sequence turn-off stars. Comparable colors. One of the next panels shows their colors. One's at about 10 kiloparsecs, one's at 15 kiloparsecs. These are relatively bright stars by the standards of the HALO7D program. These are relatively bright stars. You can see 19.3 and 20.3 in the sort of HST V band. And I'll just quickly point out a few features. You can see where is this? The calcium triplet here. This is an atmospheric, this is the A band, atmospheric, this is a telluric band, this is the atmospheric B band, H alpha. The magnesium triplet is sort of a little hard to see in detail here. This is H beta, sodium D. So one of the things if you have a sharp eye, what you may notice is the magnesium is prominent in this star, but not in this one. You can, I'll zoom in. And again, the red spectrum has a very prominent magnesium triplet. It's hardly present in the upper spectrum. These 2 stars have comparable colors. One is brighter than the other, one is closer than the other. They have, both have relatively high signal to noise. This is signal to noise per angstrom. And what you've got here, presumably, is 2 stars with different magnesium abundance. So I just want to demonstrate that we can use these spectra. I haven't done it yet, we haven't done it yet, but we can use these spectra to say something about the magnesium abundance. We can do the same thing with ion lines. With weak ion lines, we can measure the ion abundance as well. All right, that's really all I have for HALO7D. I want to switch gears a little bit and talk about comparable studies in the foreground of Andromeda. So you've all heard of the FAT survey. Someone mentioned it earlier today. This is a beautiful Robert Gendler image of Andromeda with its two satellites, NGC-205 and M32 over here, the full moon to the same angular scale. This is the footprint of this roughly 800 to 900 orbit HST program to study individual stars in Andromeda. Our big fat PI is Julianne Del Canton, but oh, thank you. You should. She'd love it, I know. Because I hate the acronym and she'd be very happy, right. So the Keck DEMO spectroscopy component of this program has been led out of UCSC, and Claire Dorman will talk a little bit about that later this afternoon, but I can't help but show this movie. This is, again, a Robert Gendler image. This time it's upside down. NGC-205 is at the bottom. But what we're going to do is zoom in, and then transition from the ground-based Gendler image to the FAT HST image, just to give you a sense of the power of the resolution of these HST data. So we're going to zoom into this blue star-forming arm, and as we zoom in, the stellar images are going to look blurrier and blurrier because we're zooming in. And there's sort of a magic moment in this movie when it switches from a ground-based image to the HST image, and as soon as the panning stops, it's going to switch. And I can watch this movie over and over again. It is an absolutely stunning demonstration of what the power of this large HST mosaic, just the power of resolving star clusters. You can clearly measure colors of individual stars. You can look right through Andromeda to background galaxies and so on. I'm not going to say anything about the science from this. There's been a slew of papers that have come out, much more in the works. A crowded field, indeed. But that raises a good point. It's a very crowded field, but you can use the HST image to judge which stars are going to be crowded or not at ground-based resolution, which is something you can't do with just a ground-based image. So that's been the basis of our spectroscopy, is to go after stars that are relatively isolated. This is not the same region of Andromeda. This is a little bit further out, but these are Hubble Space Telescope color magnitude diagrams going down to ridiculously faint magnitudes. These are studies by Tom Brown, led by Tom Brown. And what Tom noticed in these CMDs is you could use the shape of the turnoff to constrain Andromeda's star formation history. And Alice Deason suggested that some of these stars that are marked in these boxes with these special symbols are turn-off stars in the Milky Way. And you can see their brightnesses are in the range 20 to 24, a little fainter than 24. These are turn-off stars in the Milky Way. And so Roland Vandermarel, Tony Sohn, and Jay Anderson went off and measured the proper motions of these stars that are marked in blue. The stars that are marked in blue are shown in a proper motion diagram. This is proper motion along the L and B directions, galactic latitude and longitude. And you can see a concentration of Andromeda stars with relatively small proper motion, drawn from the CMD, but a distribution of foreground Milky Way halo stars from which you can measure the dispersion in the proper motion, dispersion of the proper motions. Now, we also have a handle on the dispersion in the radial velocity, and from these data, Alice suggested that while looking in the direction of Andromeda, we may have found a population of stars, small population of stars, whose proper motions are large relative to their radial motion. So something that's consistent with a shell-like structure in the Milky Way. So this is something that was published in the early part of 2013. All right. We, of course, also study the outer parts of Andromeda, and I'll show you a quick snippet of a result from Carrie Gilbert's work. This is now looking further out again, in the direction of Andromeda. Again, we encounter foreground stars, but we encounter stars in red giant stars in Andromeda, and we can use counts of red giant stars to measure the surface brightness That's what's on the y-axis as a function of distance from the center of Andromeda. And what was striking to us at the time is these data look like they go out to beyond 100 kiloparsecs. We can trace the halo of Andromeda beyond 100 kiloparsecs. And moreover, when Carey looked at these individual lines of sight, along some of these lines of sight, there were very cold velocity spikes. These 4 histograms are velocity histograms along different lines of sight through the Andromeda halo. So what she did was she tried to account for how many stars might be in these cold spikes by fitting Gaussians, for lack of anything better. And she tried to subtract off the contribution, the cold spike contribution, these kinematically cold components. And when you do that, when you subtract off the kinematically cold component, the surface brightness profile of Andromeda tightens up considerably. And I'll go back and forth. We can't do this kind of exercise. We can't carry out this exercise too far out in the Andromeda halo because we don't have the statistics. But where we do have the statistics, the surface brightness profile tightens up considerably. In other words, the kinematical substructure also is showing up as overdensities in the surface brightness profile. We can also measure metallicities, and there's a very clear trend in metallicity from the inner regions to the outer regions. These are projected radii within Andromeda. Now, these metallicities are based on photometric indices, but what we're going to do in the fall by targeting Andromeda stars in the background of Milky Way foreground stars with long Keck DMOS spectroscopic exposures is we'll be able to measure individual Fe over H and alpha over Fe for red giant stars in Andromeda for several hundred of them. And just to give you a sense, from the entire SPLASH survey, at the moment there are 4 stars in the halo of Andromeda for which the signal to noise is high enough to get any handle on alpha over Fe. We should increase that number by roughly 2 orders of magnitude by the end of this fall. All right. How much time do I have, Marcella?
6.
Okay. Thank you. Okay, thanks. I'll take 8, but that's all right. As another example of something where we can use the foreground fruitfully, this is a study, again, it's a Keck and Canada-France-Hawaii telescope study of the Virgo cluster. And what I'll talk about specifically are studies of globular clusters in the Virgo cluster, globular clusters that are satellites of dwarf elliptical galaxies. Elisa Toloba talked about dwarf elliptical galaxies. In this particular study, we are trying to get at a measurement of the average dark matter halo associated with dwarf ellipticals. The problem is the dwarf ellipticals are low surface brightness, so you can't measure their spectra, you can't measure the velocity dispersion too far out. Another problem is they're so low luminosity that they might contain 1 or 2 globular clusters each. So what we're doing is we are stacking together a sample of, in this case, 21 dwarf ellipticals with an average of 4 globular clusters per DE. We have a sample of 84 satellites. We can use that to say something statistical about whether or not these systems, these galaxies, have extended dark matter halos. So this is work done in collaboration with Elisa, Eric Peng, his former student Jingjing Chen, who is now at Columbia, Claire Dorman here at Santa Cruz, Meredith Muller, Biao Li is a grad student in Beijing. And these names in italics you probably don't recognize because they're high school students from the Bay Area who worked with us over the last couple of summers. Here's a color magnitude diagram in the direction of Virgo. This faint swath of objects contains globular clusters in Virgo. You'll have to take my word for it from this diagram, but our spectra reveal that many of the objects in this swath are indeed globular clusters in Virgo, just judging from their velocities. Now, what you also see is this hockey stick-shaped feature, which is the Sagittarius stream, and perhaps you might make out a brighter but more subtle concentration, and that's the Virgo overdensity. So again, we're using foreground Milky Way stars as fillers on these DMOS masks, and our primary science is to look at the velocity dispersion of globular clusters around DE. So this is a stacked sample of a little less than 100 globular clusters around DEs as a function of R over R effective. And you can see we can get out to several effective radii using this method. And the dynamical modeling of this sample is in progress, but it points to these things having a dark matter halo. It's not that these are dark matter free. They do have, DEs do have extended dark matter halos from this work. This is also clear from the studies of the 2 DEs in the local group, where you can use individual stars to trace the velocity dispersion very far out. This is NGC 147, 185. Marla G has done that with individual stars. But again, along this line of sight, there's a huge population of foreground stars, and I won't go into the details of how we do this, but we can identify the Sagittarius stream and the velocity of the Virgo overdensity along this line of sight. Okay, so to summarize, please stay tuned for results from the HALO7D program. We hope to be saying something meaningful about the Milky Way halo mass and accretion history, using 6D, so 3 positional dimensions, 3 velocity dimensions. The line of sight dimension of distance is the hardest thing to determine. We will almost certainly resort to a statistical treatment of line of sight distances, but the sky positions are very precise, of course, and we should have a good handle on proper motion and radial velocity. The chemical abundance will hopefully add more than 1 dimension. There will be an Fe over H and an alpha. And of course, the distant galaxy evolution from these samples should be spectacular as well, because we're talking about mostly 8-hour exposures, but up to 32-hour exposures of a nice sample of galaxies, a few hundred galaxies, to look at outflows and integrated stellar populations. And hopefully as soon as this fall, next month in fact, HALO7D will have an extension. We should get detailed abundances of a bunch of Andromeda red giants as well. And that's where I'll stop. Thank you. Questions? Yes, Sandy?
How much larger volume in the dwarf spheroidals in Virgo is probed by the globular clusters compared to the stars?
Roughly 1,000 times larger volume.
I'm talking about per galaxy.
Per galaxy, that's right, roughly 1,000 times, because we're going out to 10 effective radii instead of 1 in the integrated light. So roughly 1,000 times larger volume. Does that answer is that what you were asking? Okay. All right.
Is there any hope of seeing some of this in the fields you are analyzing, some of this very fluffy, diffuse dwarf that Hollywood won't?
The fields are very small. It depends on how much substructure there is in the halo. One of the things about going after turn-off stars is there's actually some hope of seeing things like disrupted ultrafaints. If in studies of the Milky Way halo where you're using red giants, it's pretty hopeless to look at the shredded versions of ultrafaints, because they hardly have any red giants, right? So 1, or even horizontal branch, they might have 1. So the good thing about going to turn off stars is we might have some handle on even very faint, very low luminosity disrupted satellites. I don't know if that answers your question. Yes, David?
Do you have a chance to look at the planetary nebula around these dwarfs of Virgo, and would that be of value?
I haven't, in particular. These are pretty red and dead galaxies. It's not, and they're fairly low metallicity. So I haven't looked at planetaries around these systems. There are people within the NGVS collaborations who are looking at planetaries in general in Virgo. It remains to be seen how many of them are associated with these sorts of dwarfs. They're not the best kind to look for planetaries in because of their stellar population properties. But yeah, they would be easy markers as well.
If there are no more questions for Raja, thank you very much again.
Thanks. This spring, I'll say a little bit about that, show some example spectra from that, hopefully illustrating the diagnostic power of these spectra. I'll say a little bit about how HALO7D started. It really started in the foreground of Andromeda. Splash is the spectroscopic and photometric landscape of Andromeda stellar halo, and the trash from Splash, which we've now pulled out of the dustbin, can tell us something about the foreground substructure in the Milky Way. Alice Deason talked about this on Tuesday. And similarly, in another large survey, this is the next generation Virgo survey, photometric and spectroscopic survey of galaxies in the Virgo cluster, galaxies, globular clusters in the Virgo cluster, the foreground can tell us a lot about substructure in the Milky Way. The completely white wall with just the rare nail holes spaced very sparsely. It's very difficult to judge the subtle motion of an insect. If, on the other hand, the wall is not completely white but has subtle wallpaper painted onto it, then it's much easier to look at the motion of, even a subtle motion of that insect against this background wallpaper. That's what we're using. So that's why one of the epochs needs to be deep to map out the background galaxies. We expect to measure proper motions for about 1,000 main sequence turn-off stars in the Milky Way halo, ranging in distance from few or 10 kiloparsecs out to over 100 kiloparsecs from the sun. This is an incredibly subtle measurement, but HST has done this. So I'm going to talk about a project called HALO7D that's just starting out. So I won't have a lot of results. I'll talk about a project that promises to produce exciting results. This all started because I made a discovery a few years ago that we live inside a galaxy. When that happened, I started to look at some of the foreground things that we were throwing away otherwise. And so I'll talk about the HALO7D project, but I'll also give you a few related examples. The main theme of the HALO7D project is the Milky Way's stellar halo. And if we can measure the motions of individual stars in the Milky Way stellar halo, 60 motions. 60 phase space, positions, three positional dimensions, 3 velocity dimensions. Then we might have some handle on using them as tracers of the dark matter halo. We also want to use these stars to look for substructure, try and understand the accretion history. And in the process of doing this, the spectra we're taking are going to tell us something about the chemical abundances of the stars, not just iron to hydrogen, but also the alpha to iron ratios. So I'll briefly touch upon 3 ongoing studies. Like I said, the HALO7D survey of the Candles fields that many of you know about kicked off this. All right. So there are 2 components to the HALO7D program. There is an HST archival legacy program that involves taking literally every field for which HST has taken deep multi-epoch images with its new cameras. We're not using WIFPIC 2 or WIFPIC 1. We're using ACS and Wide Field Camera 3. As long as there's a baseline of 5 or more years, and as long as one of the 2 epochs is deep, then we can abuse the distant galaxies in a particularly special way here. We can use the background galaxies as wallpaper, and it's like it's analogous to trying to watch an insect crawl slowly across the wall. If it's